Therefore, these two together show us that the expectation is a linear operation for any a1, a2 real numbers. Um, as you see, this is a generalization. Here, g1 and g2 are just two arbitrary functions that you can apply to random variable x. A1 times g1 of x plus a2 times g2 of x is going to be equal to a1 times the expected value of g1 of x plus a2 times the expected value of g2 of x. This is the most general form that you can express the linearity of expectation, which is a demonstration of the superposition principle. Okay. So next, we will look at the variance of these two expressions, x plus a and a times x. Well, we have an idea about what these should be, because when you shift the distribution, for instance, you just shift it by some amount. You do not touch the distribution itself. You do not touch how the outcomes are positioned with respect to the mean, because with the distribution, the mean is also shifted, as we have just seen. Therefore, the variability of the distribution, the dispersion of the distribution doesn't change. So we expect the variance to be kept constant with respect to a shift operation. So let's see how that plays out. The variance of x plus a, by definition, this is the second moment of x plus a, which is a random variable. X plus a is a function of random variable x, so we can see it as a random variable by itself, minus the square of the mean of x plus a. Okay, if you expand this x plus a squared, you get x squared plus 2ax plus a squared minus, we have just seen that expected value of x plus a is expected value of x plus a. So you just plug that in, okay, and expand that square, you get expected value of x squared plus 2a times expected value of x plus a squared, right? And this is, well, you can just separate these three terms in this expectation. And when you arrange them, this cancels out with this, and a squared cancels out with this. And what you have is second moment of x minus the mean, the square of the mean of x, okay? Which we know to be equal to the variance of x, which means a shift operation in any distribution does not affect the variance. And this is also consistent with our knowledge of the variance, because remember, variance is the second central moment, okay? Central moments, remember, are moments defined with respect to the displacements from the mean. Therefore, any central moment, not only the variance, which is the second central moment, but central moments of any order will not be affected by a shift in the distribution. Now let's look at the scaling of this distribution, a times x. Let's consider this. Remember, the expected value of a times x is a times the expected value of x. So what about the variance? Let's see what happens to the variance in this case. Just apply the definition, the random variable a times x minus its mean, expected value of a times x, squared, and the expectation is taken of this expression. And you see this expectation I can write as a times the expectation of x. And you see I have a times x minus a times expected value of x. I can take it in the common term a parenthesis. And therefore that will be a squared times x minus the mean squared. Okay, and a squared here is just the constant term. I can take it out of the expectation here. Okay, and what remains here is the variance. So this is equal to a squared times the variance of x. Okay, so this is true for any distribution. If you scale random variable x by a, the variance becomes a squared times the variance of x. And of course, when you look at the standard deviation, it's equal to the square root of the variance. Therefore, the standard deviation for the scaled random variable a times x is equal to the standard deviation of x multiplied by not a, But since square root of a square is equal to the absolute value of a, be careful when a is negative. This should not be negative because standard deviation cannot be negative. Okay, so the standard deviation is also scaled by the absolute value or the magnitude of a, let's say. So therefore, you see, for any random variable, if you shift it by its mean, the mean becomes zero, obviously, because this is the first central moment, which is zero for any distribution. What about this? The variance of this is x minus its mean scaled down by the standard deviation. The variance of this becomes 1. Remember, this is the standard variance. Okay, this is the standardized random variable x minus its mean divided by its standard deviation. This is the standardized random variable, and this standardized random variable always is zero mean, and it always has a variance of 1, which follows from this discussion here.